Okay, so today we're going to start talking about arithmetic and geometric sequences. So we saw before sequences is like when you get a pattern of numbers and there's a rule to it. So what we're going to see, there's what we call arithmetic and geometric sequence. An arithmetic sequence, so one that could be an example of that, would be if you have, so you'll have your VO. So I'm writing it in a recurrence relation. So you might say that's 10. And its rule would have, so the way I get the next one would be maybe you add 10 to the one before. So arithmetic means that you either are adding or subtracting a certain amount, yeah? So it's like that. When you have a geometric sequence, an example of a geometric sequence will be, so you'd have your VO, I'll just use the same one, but the rule, you'll see that you are timesing it by something. So I might say 1.5 times Vn. So if you're timesing something by more than 1, can you see that the value would be growing? Isn't that true? If you times something by more than 1, you get a bigger value the next one. If you times something by less than 1, so if I times something by 0.5, doesn't it go into smaller numbers? Yeah? So we're going to look at that. But the main thing is to see is that a geometric one, you have a timesing thing. So it could be getting bigger or smaller depending what we're timesing it on. Okay, so if we have a look here at the arithmetic sequence, so I'm looking up here. So as I said, it can be found by you're adding a common difference. So if you have a look at it, if that's like here, so if I'll put an example, keep doing that. If I do an example and I have Vn plus 1 equals, and I did Vn plus 2. This one is an example of growth. Isn't it getting bigger? Yeah? And the common difference, so this common difference is that plus 2. That's the thing that's changing every time. If I did another rule, if I found the term and it was, say, minus 3, can you see, we call it decay or it's depreciation because it's getting smaller every time, isn't it? But the common difference is you're adding minus 3. So can you see how it's an arithmetic, but you're doing the same thing? When you look at these graphs, if it's an arithmetic sequence, so if we've got an arithmetic sequence, can you see that the graph is straight line? So an example of that is simple interest. So you've got simple interest, and that's an example of an arithmetic sequence that is growth. So you might write that that's a growth. When you have an example of an arithmetic sequence where it is decaying or depreciating, is flat rate or unit cost. And that's an example of decay here. So what it is, it's always the same amount. So here you might write the same amount increased every time, yeah? And then with these two down here, it's the same amount decreased every time. So we're going to look at that. We're going to look at these individually, and arithmetic will be the one we look at first, but just so we can compare and we can see. So later on, we will look into the geometric sequence, and you can see that you are multiplying by a common ratio. So if I do a couple of examples here, so Vn plus 1, if I did 1.2 Vn, this is an example of growth because the number would keep getting bigger. Now, can you see if, say, you had $100 and you times it by 1.2, you get 120. Then if you go to do the next term, it'd be 120 times 1.2. So can you see you actually, and then you would be increasing it by 24 on the next time. See how the amount that it's increasing will be bigger and bigger and bigger and bigger. That's what geometric is. It's not always the same amount, which is why we get a curved. So it gets bigger and bigger, the amount of interest or gain that you're getting. So if you have a look here, the common ratio is that bit there. That's the common ratio. So if we have growth, the number is more than 1. If I had an example of decay, you will see a number less than 1. So I might say 0.7 VN. That would be a decay, because this number is less than 1. So that number there. Okay, and that's the common ratio. So you can see there's a few examples. So an example of growth in geometric is compound interest, and an example of decay is called the reducing balance. So we'll go through all of these individually, just so you know. So just to go over an exam question there on this stuff, there's one. It says the following recurrence relation will generate a sequence whose value is the following will generate a sequence whose growth arithmetic. Now, can you see this one? It's like they're missing the question. Right, so if you look at these ones down here, can you see this is a growth, an arithmetic, because we're adding the same amount. So that's okay. That one is true. That's an arithmetic. Can you see this is a decay arithmetic because the same amount is being subtracted every time. And now you can see geometric. This one would be geometric growth because it's bigger than 1. And this one is a decay geometric because it was that. So we'll have to, I'll say, I think this one was missing a graph. You had to say which one it was. Okay, so now let's look more closely at linear growth or decay. So when we say linear, that's just another way of actually saying arithmetic as well. So linear or arithmetic sequences. So we're going to look at that. So as we know, it's a straight line. So if you see there, we said it's a straight line. So we either have a graph that's going up with growth, or you'll have a graph that's, a line that's going down. Okay, so in linear growth, you'll see that the sequence increases by the same amount. So that same amount is this D there. So they call it the common difference. And it could decrease, so that was increase, or decrease by the same amount, which is that D there. So, as I said, you have a fixed amount of interest that's paid at regular intervals, and the principal. So we're going to start talking about simple interest or flat rate decay or unit cost decay. And they'll say the principal, which is always going to be your VO there. So you're going to know that principal is your VO. So that will be your starting term. So when they say we got a loan of $100, that's your starting term. And the amount of interest that's usually added, that will become your common difference. So we're going to look at some examples. So if you have simple interest here, you will have a recurrence relation that follows this pattern here. So if you're asked to set up. So we know VO is your initial amount, and you know that you need to be able to find this D. And here's the formula to find D. So what you're going to do is you're going to take the rate, the interest rate over 100, and then times it by your initial. So let's do this little example here together so that we can do it. So if Michael gets a loan from the bank for $7,000, so I often like to start doing this above my question. So I've got VO, and is charged a simple interest rate of 7.4% per annum. So they've just given me the rate. And here that means per annum, which means every year. They're giving you, we often call it the N. So N is how many times a year. So we're going to say 1 times a year. Okay, so it says model this scenario using Vn plus 1 and Vn. All right, so a recurrence relation means we always have to do what we said yesterday. So we've got to write down VO if they're asking us to write a recurrence relation. So I'll write VO, and I know that's 7,000. And now I have to write the rule, which I can see up there should follow this pattern. So Vn plus D. So I really just need to get the D value. So over there in the purple, you can see that we've put how to find D. So it should be R. Now I like to write divided by N because we should be thinking about whether it's monthly or yearly. So, and then write over 100 and then times VO. So if I look, I had 7.4 divided by 1 over 100 times 7,000. So what we're going to see when you do that, on your calculator, you should get 518. So every year, 518 is going to be added to this simple interest, or this loan. So he's actually loaning. So every year, if he doesn't pay anything back, he's going to have to pay he'll pay $518 for every year he has this loan. So for me to actually go finish off this recurrence relation, I should have Vn plus 518. So what the examiners are looking for is for that to be written and that to be written. Okay, so that's a recurrence relation there. So it says use the recurrence relation to find the value of the loan after 1, 2, or 3 years. So I would think that you would want to use this method on the calculator. So can you see that's what we were doing yesterday, where we said, remember we put this, we put the 7,000 in, pressed enter, and then when you said plus, it'll say answer, and you plus 518, and then you count it through. So when it says after 1, 2, or 3 years, this is 1 year, this is 2 years, this is 3 years. So we're going to say the answer. So it wanted you to write them all out, so you can see I've written them out there. I would not worry about this method. We don't need to do that. Okay, then it says use your calculator to find out how many weeks it would take to get to 10,000. So what we're going to do, I'll flick back on the calculator and we'll practice what we did yesterday, and we'll just count how many years it takes to get there. So we see that it says 6 years to get to, and we're going to say it was roughly 10,108. So we did this using our calculator method. Now, because we better be careful, we need to start really looking at questions. It did say weeks, so I might just go therefore 6 times 52, because there's 6 weeks. We're just going to say roughly. That was probably an error in the question, but we'll just say 312 weeks. Why did I write 52? Because there's 52 weeks in a year, yeah? All right, so then here's another example. It says write down the recurrence relation model if 15,000 was borrowed. So see there's VO and was borrowed at a simple interest rate of 3.8% per annum. So you can see I've worked out the D here. I found out it's 570, and so therefore I've written out my recurrence relation. I put the VO and then I write how do I get the next term? I do Vn plus 570 because that's what we found. If we went D, we went 3.8 divided by 100 times 15,000 gave us the 570. Okay, so there was another example. Okay, so what's going to happen? What if I said find out what happens after 52 years or something? You do not want to be on the calculator pressing enter, enter, enter 52 times. So we now need to come up with a rule that helps us get to a particular spot straight away. that's called, on the next page, that's called finding the nth term. So if they ask for a recurrence relation, that's when you do the VO, Vn plus 1. If they ask you for the nth term, this is the formula we are going to be using. So you can see we are nearly all the time given the VO, and N will be how many years or weeks they want us to find, and D is that common difference. So if you have a look, if we know the way we find D was here, you do the rate over 100 times VO. So I could write this formula out like this, and all I have done there is that this bit here is the D, isn't it? That's that D bit there. Okay, so we've got an example over here, so let's go through that one together. Use the example up here. The following recurrence relation can be used to model a simple interest investment. So VO, that means they invested $3,000, and every year they're getting $260, aren't they? So it says, what is the principle of the investment? So can you read this and tell me what was the principle? What did they first invest? Yep, and that's all you need to write. Good. 3,000. What is the interest rate per annum? No, that's not a rate. So 260, you know that D equals 260, don't you? Yeah? Now, you know the formula for D is actually R over 100 times VO. Isn't that true? And I'm going to say it equals 260. Can you see I just put the rule for D there? This bit is just the rule for D. Yes? Now, if I know that, do I know what the VO was? What was VO? 3,000 and equals 260. Can you see that I only have one thing I don't know in that formula? What is it? The rate, which is what I want. So what can put into my calculator is solve, comma, R. So let's go do that. Okay, so we got R equals 8.7%. Okay, so what's the interest rate per annum? There's our answer. And then the next question, write down the rule, for the value of the investment after n years. So I don't want, this is the recurrence relation. This is not the nth rule up here. So what I need to do is write it like this way. So I'm going to write Vn equals, now I'm not going to write VO. What's VO for me? So VO is 3,000 plus, I do whatever times years, so N times, and what's D? 260. Now, we don't normally write the letter at the front, do we? So what we probably will see will be Vn equals 3,000 plus 260N, okay? So can you see I'm doing like up here, and there, that was my VO, and that is the D. So I've substitute that in. That's the rule for the nth term. So when will the value of the investment first exceed? So what you want to do here, when they say when, obviously N is the question. I want to know how many years or how many, this is years, it's going to take. And this, they're telling me a value. So if I sub that into my nth term formula, I would say 10,000, equals 3,000 plus 260N. And once again, I can do the solve function, and I'll do comma N to find out how many weeks. So I'll do that. So I get N to be 26.9. So I'm going to say, therefore, after, I'm going to round up and I say 27 years. They will probably be more direct in your exam and tell you, they'll say round to years, not and they're very clear on what they want. So over here, sorry, we didn't do this one. It says, use the rule to find the value after 15 years. So that means n equals 15. So what you want is V15. And you just told me a rule on how to find an nth term. So what I'm going to do, see how I have now written where n is 15? So that means this will become 15. So it'll be equals 3,000 plus 260 times 15. And you'll do that, which will be... okay, so that ends up being 6,900. So that's the value of it. Right, so let's have a look. We'll go through this one and you can write out what's missing. But let's have a look first. So Arnie invests 4,000. So you should start getting a good habit of writing things above it. It makes life easier because sometimes you might not even know what they're asking, but by the time you put all these little points there, you'll get it. So he invests 4,000. Now, it's also vital that you're highlighting this thing because at the moment, we're all doing simple interest. But in the exam, you're going to have mixed questions. So we need to highlight that we're doing simple interest. So I know that you're going to go to simple interest formulas to do it, yeah? So we go, Arnie invests 4,000 in simple interest investment and we're going to write 65% per annum. So the per annum is also very important because you're going to say, they will always quote the per annum, but they might say the rule needs to be in monthly, but at the moment, so that's R. So find a rule for the value of an Vn after n number of years. So that's good. They want a yearly formula. So if you go and look at simple interest and what they've just said then, they want the nth term rule. So here I've written out the formula. This is the formula that we use to find the nth term. Nth term formula. So into it, that's what I'm going to do. So Vn equals, now I need to substitute in VO, which is 4,000. So I've done that. Plus, and it will be n times the rate. So you can see I've put 6.5 in there over 100 times 4,000. And here we end up with the nth term formula. That's what it'll look like. Then it's asked me what is the value of the investment after 10 years. So n equals 10. So you can see I've put 10 is the one I want. So where I saw n is where 10 has been put, and then you get your answer.